This example comes to section 3.5, related rates. Sometimes for me the hardest part is writing out this great big thing. So a bright flashlight on the ground shines on a wall that's 15 meters away. A man 2 meters tall walks from the light to the wall at 1.4 meters per second. How fast is his shadow on the wall decreasing when he's 4 meters from the wall? Definitely a situation where I need some kind of a picture because it's hard to even imagine what's going on here. I've got a light, it's sitting on the ground. I've got a wall over here that's 15 meters away. So the distance here is 15 meters. That light is shining on the wall, so it's going to create some kind of a bright spot there. But then I have a man here that's in the way, who's walking along, and he is 2 meters tall. And he's walking along in that direction at 1.4 meters per second. So it's not as obvious what my equation or what my relationship between variables is, because really I haven't made a variable yet. Let's call this his shadow, because if that man is standing in that spot, he's going to create a shadow, block the light out here. So we know that 15 meters is an unchanging value. The light is not moving any closer to the wall. It's staying exactly where it is. And the man is 2 meters tall. That's an unchanging value as well. So those are true numbers. But we don't know all the time how far he is away from the light or how far from the wall. So in my situation here, I'm going to call this x, just so that I have something to name it. And I know a couple of things. I know, first of all, dx by dt is 1.4 meters per second, because he is walking away from the light, so that x that as I've defined is getting bigger, so that's a positive rate. ds by dt is what I'm trying to find, and I'm asked about the instant when he's how far away from the wall is he? 4 meters from the wall, which means x equals 15 minus 4, which is actually 11 meters. So be a little bit careful about that, because I did say that he's 4 meters from the wall, not from the light. The relationship here between the variables actually has to do with triangles. Just saying, well, s over 15, that big triangle that has the shadow here and the 15 here, should be equal to 2 over x, because, again, opposite over adjacent if you're looking at the angle there at the light, but the ratio should be the same. 2 over x should be the same as s over 15. So what you do from here is you take the derivative of everything with respect to time, because you now have a relationship between the variables with only s's and x's, which is perfect. And so on the left side I'm going to get 1 over 15 ds by dt equals negative 2 over x squared dx by dt. You could write 2 over x as 2x to the minus 1 if you prefer, but this is what you end up with. So I just have one unknown thing, which is ds by dt. So ds by dt should equal negative 30 over x squared dx by dt. So if I put in my values, ds by dt is going to equal negative 30 over 11 squared times dx by dt, which is 1.4. And so, you might get a big fraction here or decide to change it to decimals, but just calculate that out. So if you're leaving it in fractions, your shadow is changing at a rate of negative 42 over 121, and the rates here would be meters per second, or negative 0.35 approximately meters per second. Again, depending on whether we wanted exact values, which is usually the case, or if they said round to the nearest hundredth or something to that effect. But it makes sense that as that man walks closer to the wall, his shadow will get smaller and smaller as the man walks further up here. His shadow will be smaller on that wall, and so it's shrinking as he walks towards the wall.